The boundaries of human computation are hidden inside the cartridges of our favorite video games. The Millennium Prize problem of P versus NP is not just an abstract mathematical puzzle. It is the invisible engine that dictates why a game is engaging. We are entering a world where the Mushroom Kingdom and Hyrule serve as the ultimate proving grounds for theoretical computer science. Prominent theories in game design suggest that fun arises when we face challenges that are difficult to solve but easy to verify. This psychological hypothesis posits that the human brain craves heuristic optimization. We are not just playing, we are literally training our minds to navigate NP-hard combinatorial spaces in real time, finding patterns where a brute force computer would struggle. To analyze a game, we abstract it into a generalized decision problem. NP covers games where a winning sequence is quickly verifiable. NP-complete games are the hardest problems in NP. Co-NP involves proving a move is safe, like in Minesweeper. PSPACE governs games with reversible mechanics, requiring only a polynomial amount of memory to solve, even if they take exponential time. Finally, EXP time covers the vast decision trees of games like chess. Cognitive apprenticeship uses games to make abstract theory visible. Instructors model logical reductions using recognizable game mechanics. Students then construct their own logic gates within these digital worlds. Because the game engine strictly enforces its physical laws, it acts as a scaffold for rigorous proof. Eventually, the game metaphor is removed, leaving the student with a pure mathematical understanding of intractability. To prove a game is NP hard, we must translate a known complex problem, like Boolean Satisfiability, into the game environment. This requires building functional logical circuits out of level geometry and simple enemy behaviors.
This translation relies on local structures called gadgets. Start and finish lines define the entry and exit of our proof. Variable gadgets force the player into irreversible binary choices, such as falling down one of two pits to represent true or false. Clause gadgets act as physical locks that only open if the player arrives with the correct items. Crossover gadgets allow logic paths to intersect without interfering with one another, a massive technical challenge in two-dimensional games.
In Super Mario Bros., we map logic directly to the Mushroom Kingdom. A player dropping down a shaft represents a variable assignment. Carrying a shell is like a signal traveling a wire. However, if we include reversible elements like P-switches or vines, the game's complexity jumps from NP-hard to PSPACE-complete, because the player can now manipulate and revisit different board states indefinitely. The Legend of Zelda series shifts the focus to spatial dependency. While items like the hookshot provide conditional movement, it is the block-pushing puzzles that define its complexity. These puzzles are isomorphic to Sokoban, which is proven to be PSPACE-complete. This means that while Link only needs to track a few variables, the number of possible configurations he must navigate can grow exponentially relative to the size of the room. Even menu-based RPGs like Pokémon are deep computational puzzles. By using the line of sight of non-player trainers as logic gates, researchers have shown that navigating a route without losing is NP hard. If the battle logic allows for complex state changes, generalized versions of these RPGs can even reach PSPACE completeness, making the search for an optimal path a monumental task for any algorithm. Minesweeper illustrates the gap between NP and co-NP. Determining if a board has any valid mine placement is an NP-complete consistency problem. However, asking if a specific square is safe is an inference problem. You must prove that no valid configuration exists where that square contains a mine. This makes the player a real-time theorem prover for co-NP-complete problems, explaining why high-level play feels so mentally taxing. When players attempt to finish games as fast as possible, they transform simple decision problems into extreme optimization problems, pushing against the physical limits of computation. Routing an open-world speedrun is a dynamic traveling salesman problem, where every item collected can change the travel time to the next. Even tool-assisted runs cannot brute force a perfect solution, as the search space of possible inputs is larger than the number of atoms in the universe. Furthermore, Managing health to gain time-saving damage boosts is a direct application of the NP-complete knapsack problem.
Here is the definitive map of game complexity. While Tetris and Candy Crush are NP-complete, generalized versions of Mario and Pokémon escalate to PSPACE-complete when reversible mechanics are introduced. Zelda, Lemmings, and Portal sit firmly in the PSPACE category. This hierarchy shows that many of our favorite games are not just difficult for humans, but are fundamentally challenging for any possible computer.
This research reveals a profound mathematical truth. If an AI could play PSPACE-complete games like Zelda or Portal optimally in polynomial time, it would prove that P equals PSPACE. This would be a more radical result than proving P equals NP, as it would mean that space and time are computationally equivalent. Our play is a daily encounter with the most profound mysteries of the universe.